Hello, my name is William Chalk, and today I will be showing you how to solve question number 13 on page 331 of the Nelson Advanced Functions textbook. Here I have the question written out. You are given cos of theta is equal to negative 5 over 13, where 0 is less than or equal to theta, which is less than or equal to 2 pi. In which quadrants could the terminal arm lie? Determine all the possible trigonometric ratios for theta, and state all the possible radian values for theta rounded to the nearest hundredth. If we go to highlight the most important parts of the question, we want to recognize that we are initially given cos of theta. The value is negative, and then we want to find which quadrants the terminal arm could lie in, all the possible trigonometric ratios, and all of the possible radian values. Keys to solving this question are determining which triangle theta is a part of and the side lengths it has, and how theta is represented on a cast diagram. To solve part A of the question, we must find which quadrants the terminal arm could lie in. So here I have written out our initial equation, and I have our cast diagram. Now, we know over here that cos of theta is negative 5 over 13. So we must find the quadrants where cosine can be negative. If we go to our cast diagram, we can see that in the C quadrant for cos, it's going to be positive. In all, cosine is going to be positive. In sine, cos will be negative. And in tan, cos will be negative. So we know that, of course, it cannot be anywhere that cos is positive, and therefore must be in quadrants 2 or quadrants 3. The next step in the problem is to find all of the trigonometric ratios for theta. To do this, we must first find all of the side lengths of a right angle triangle that contains the angle theta. To start out, we'll label one of the angles on a right angle triangle theta. Now, we know that cosine represents the adjacent side over the hypotenuse. So, we'll take 5 and label the adjacent leg, and 13 and label the hypotenuse. Now, we just need to find the remaining side. To do this, we'll use Pythagorean theorem. As we can recall, a squared plus b squared is equal to c squared. Now, we already know c, which is 13, and b, which is 5. So we need to rearrange the equation to solve for a. So a squared is equal to c squared minus b squared. Therefore, a is equal to the square root of c squared minus b squared. So now we will solve for the side length a. I have a little reminder diagram in the bottom here, and I've copied the equation back up here. So a is equal to c squared, which we know is 13 squared, minus b squared. We can continue to solve this, bring up the calculator. 13 squared is equal to 169, minus 5 squared, which we know is 25. (169 minus 25 is equal to 144. And the root of 144 is equal to 12. Therefore, the final side length on our triangle is 12. Now that we have all of the side lengths of our triangle, we can find the trigonometric ratios for theta. So we already have cos, meaning we need to find sine, tan, secant, cosecant, and cotan. So, first sine theta. Sine of theta is equal to the opposite side over the hypotenuse. Therefore, 12 over 13. But as we can recall from before, theta can either be in quadrant 2 or quadrant 3. In quadrant 2, sine of theta will be positive, but in quadrant 3, it will be negative. So, sine of theta can also equal negative 12 over 13. Next is tan theta. Tan of theta is equal to the opposite side over the adjacent side. So, 12 over 5. And for the same thing as sine, it could be positive in quadrant 3 or negative in quadrant 2. So it can also be negative 12 over 5. And now we get down to our reciprocal ratios. Secant of theta, cosecant of theta, and cotangent of theta. The first, secant, is the reciprocal of cosine, meaning we can just take the reciprocal of cos of theta, which we already have. So 13 over 5, and it's still negative. Cosecant is the reciprocal of sine, so 13 over 12, or negative 13 over 12. And cotan is the reciprocal of tan, so 5 over 12, or negative 5 over 12. And that is all of our trigonometric ratios for theta. Moving on to part C of our question, we need to find all of the possible radian values for theta. To do this, we must first find all of the possible radian values for the related acute angle alpha. To do this, we'll write out the equation cos of alpha is equal to positive 5 over 13. This is because all trig ratios in the first quadrant yield a positive value. After this, we simply rearrange to solve for alpha. So alpha is equal to cos inverse of 5 over 13. Now we just bring out our calculator and put that in. Cos inverse of 5 over 13 is equal to 1.1760. We'll write this up at the top for later. Given alpha, we can now use the cast diagram to solve for theta. So if we draw out our cast diagram and a terminal arm in each of the quadrants that we know theta can lie in, and label our related acute angle, we know that this angle here will be alpha and this one here will be alpha. Further labeling the cast diagram, we have 0, 0.5 pi, pi, 1.5 pi, and 2 pi. So our first value for theta will be this angle here, and our second will be this angle here. To find the first value, we can simply take pi, subtract our related acute angle to give us theta. And for the second, pi plus the related acute angle equals theta. Now, all that's left in finding the radian values for theta is to plug numbers into our calculator. So, for our first one, we'll take pi minus alpha, which is 1.1760, which is equal to 1.9. Now, we are going to the nearest hundredths, so we're going to round up to 1.97. For our next value, we need to take pi plus alpha. So pi plus 1.1760 is equal to 4.32 rounded to the hundredth spot. These values here are all of our possible radian values for theta over the domain 0 to 2 pi. Use of these trigonometric concepts are used widely in the field of surveying. Surveying land, typically for the purpose of preparing for a building to be built, consists of using measurements from various reference points and trigonometry to provide accurate models of an area.